It's my pleasure to introduce Alberto Caron from the Alan Turing Institute, who will be today's BSU seminar speaker. And the floor is yours.
Thank you very much. Thanks, Pantelis, for inviting me. Yeah, my name is Alberto, and I work at the Alan Turing Institute. I was a PhD, before that I was a PhD at UCL Stats. I did my PhD in causality and causal inference. At the Turing, I'm now affiliated, I'm doing something a little bit different. I am affiliated with the AI for cyber defense team. The team is a bit heterogeneous, so there's a lot of people doing cybersecurity, but then there's also there's a bit more like hybrid people doing a bit of ML and for cybersecurity, and then there's people like me who are statisticians by background and try to do a bit of statistics applied to cybersecurity problems. So probably not the most biostatsy work, this one, but hopefully we'll find some overlap. Well, I'm happy to get questions throughout the talk, so interrupt me anytime. We can play this little drinking game. Every time you ask a question, I take a sip of coffee. I swear it's coffee, by the way. Right, so the work I've been doing for the past couple of months now is on, model-based reinforcement learning. In general, people, yeah.
First, direct this.
Oh yeah, sorry. Move this away. Better? Yes. Yes. So yeah, so I've been working on model-based reinforcement learning. In general, people in my team are interested in sequential decision-making problems, and they're using different types of solutions that span Bayesian optimization to pure RL, model-free RL, and model-based RL. Which one they're using depends a bit on the setting, whether they have good simulators so they can actually generate data, or like good test bed tools for the type of cybersecurity problem they're trying to solve. I'm also trying to pivot a bit around this idea of like sequential experimental design, because what I've been doing is specifically efficient exploration in model-based reinforcement learning. We will get into this and how to tackle purely explorative tasks in reinforcement learning through like non-myopic and also like scalable, so not computationally cumbersome methods. This presentation is obviously intended to be a very high-level overview of the stuff. So again, interrupt me at any time if you have any question. Right. So this is the first slide is just kind of like introducing what's Bayesian optimal experimental design. I know that probably most of you actually already seen this enough times. So basically, the whole BOAD-ED setting is a setting where we're trying to design an experiment and pick an experiment that is optimal in terms of reduction in uncertainty in the posterior distribution, given a certain prior distribution. So we have our prior B theta, and we have some probabilistic model of interest that's on like an outcome Y given theta, and B, which is a design choice, which is this like undisclosed quantity that is basically up to the designer to pick. And of course, we want to, as I said, like reduce the uncertainty around this the posterior distribution, the parameter theta in general, and this is obviously for single step. I'll try to move this a bit more out of the way. doesn't go more this, but up on top you can help?
I know. That's because you have the titles there, so it might be the. Yep.
The pad is not really helping me. Okay. Okay, good. Cheers. Good pick. Right. So, oops. That was the so that was the single stage case where we sorry, yeah.
How would you know things about if there was a cost associated with different designs?
That's an interesting question, and I think there are ways of doing that. At least there's going to be like a last slide, which is about some future research that we're trying to pursue, and one of that is constraint-based dynamic optimization, which is something like in a setting where you have a cost function, you can clearly define a cost function, so you can actually have a constraint type of optimization around the quantity of interest. I'm not particularly sure about the experimental design case, but it's something that people care about in RL because, like, mostly like in robotics, for example, you always want to add some like boundaries to exploration to kind of like guide to have some sort of like principled safe exploration. But there are ways I think of like adding a cost functions, well specified cost functions around the optimization in general. I might have to double check though. Anyways, so that was the one step simple case. In sequential experimental design, people generally attempt to do this iteratively. So they try to like optimize at every given step. So the posterior from the previous stage becomes the the posterior becomes the prior, yes, and so on and so forth. So you have to carry out basically the computational effort of computing a posterior distribution at every step, and also the optimization of the reduction in entropy at every step, which can be quite burdensome. So it depends which settings actually allow you to do the computation, the full computation. I'll start with a bit of a primer of what is reinforcement learning and how this is formalized through Markov decision process. So RL is typically a cabinet of tools to solve dynamic sequential decision-making problem, where you generally have an entity called an agent that takes actions in an environment, and the environment catapults it into the next state and giving some reward or like utility function based on the action and the state that the agent is in. This is obviously well formalized, better formalized through Markov decision processes. So these are basically like processors. Markov processors are augmented with some kind of like decision variable, which is the action. So we have some state space that is given to the agent, action space, which is a action that the agent can take. Then we have some form of a transition probability distribution that governs the Markov dynamic of the MDP. We have some initial state distribution that determines where the stage is, where the agent is dropped within the environment. Then we have some like utility or extrinsic reward function that rewards the agent and sort of like itself defines the task that the agent is trying to solve. And then we have some discount factor that sort of like balances out short-term rewards with long-term rewards. The whole idea behind the RL and Markov decision process is that the goal is to find an optimal policy An optimal policy is an optimal sequence of actions. The policy might be deterministic, but it's mostly most of the time is actually stochastic. So it's actually a distribution over the action space. And an optimal policy is a policy that maximizes a class of value functions and discounted returns. So these are in order the action value function. So it's a function that determines the sequence of rewards, the future discounted sequence of rewards given by plain action A in state S. The value function is just marginalizing over the actions. So it just determines the value of a single state. And then we have the discounted returns function, which is just the sum of discounted average rewards given by a policy. Notice that these are all parameterized by a policy. Sorry, these are all functions of a policy pi. So each policy actually triggers obviously different functions, value functions. So one of the long-standing issues or like challenges in reinforcement learning is the exploration exploitation problem. So obviously, exploration is essential in I would argue probably in all optimization problems because the sort of issue is that you might get stuck in suboptimal policies, like you can get stuck in local optima when you're trying to optimize some function for some loss function, and so on and so forth. So exploration is generally beneficial in RL, even when the extrinsic reward function, so the utility of the agent is well defined, because the state and action, the Cartesian product of the state and action space might be I-dimensional. So it's always kind of like hard to find I rewards region, even when rewards are well defined. Then there are other like problems, which are actually the ones that we are trying to tackle, that are purely explorative tasks in RL. So this is a quite nice example that I found this morning, but this is like basically a representation of a Mars rover. So a Mars rover is just purely trying to explore an unknown environment in a very efficient way. So this is like this type of settings, you have essentially zero extrinsic reward. So you like the agent actually doesn't really get any reward from the environment per se. So you have to define a sort of like reward utility function yourself. Right. So you might have noticed that this actually bears some similarity with sequential experimental design, in a sense that designing exploration policies is similar to designing good experiment choices, but there are some subtleties between subtle differences between them, because one is actually happening in a dynamics environment, while the sequential experimental design, is not necessarily always taking into account this dynamic in the environment. So there has been some recent literature that sort of like looks at one side of the coin, which is actually how can we frame the sequential experimental design problem as an MDP, so we can actually design policies that maximize the set object, and the other stuff that, like the other side of the coin, so stuff that we were trying to do is how we can use principles from experimental design instead to design good exploration strategies in RL. And the main problem with the existing set methods is that they don't scale well when you have big MDPs. And by big, I mean like state and action spaces that are quite combinatorially big, or again, they don't really harness the environment dynamics to sort of like look at what the downstream effect of an of an action could be. There are also like other there's also overlap with other fields such as Bayesian optimization and Bayesian active learning. So in Bayesian optimization, you're trying to maximize Bayesian optimization is probably the most similar one to exploration in RL, because what's happening in Bayesian optimization is that you're trying to maximize a black box function by efficiently sampling from region of the function. So the objective is not purely explorative in the sense that you're trying to hit the maximum of that black box function with less samples possible. So you're again trying to balance out exploration exploitation. Bayesian active learning instead is purely looking at like prediction accuracy of a model. So for example, and it's looking at like label sampling. So for example, if you have a set of if you're trying to like do online training of an image classifier, then you might have some new samples that need labeling, and then you can actually like basically use Bayesian active learning principle to choose which one of the sample to label that gives you the maximum like gain in prediction accuracy. So it's all like sides. There's a lot of overlap between these. So the way that this exploration problem is tackled usually in reinforcement learning is through intrinsic motivation. So intrinsic motivation is just basically augmenting the reward signal from the environment with some like internal or intrinsic reward signal that is that could be based on different stuff. So a very naive way is count based. Notice that also this is actually reactive in the sense that, for example, if we pick the count based methods, we're trying to basically augment the reward signal of the agent with some measure of visitation frequency, such that we upweight less visited regions of the state action space. And this can only be done in retrospect. So like once the agent has bumped into these new states, can actually retrospectively look at it and score like, oh, this is actually something, this is a state action pair that I haven't seen many times. So I try to basically like change my utility function to nudge the policy to explore those regions. There's another set of intrinsic motivation bonuses that looks at empowerment. This is typical in, it's not really like for exploration, but it's typical in robotics settings, where you use basically a intrinsic reward that is based on the on this like joint mutual information, which basically signals how much control the agent has on a certain state, and tries to basically like incentivize the agent to be in state where it has control of the transitions, more control of the transition. And then there's possibly the most popular one, and the one we are looking at is model-based intrinsic motivation. So model-based basically just exploits some form of like dynamics model, where the dynamics model is basically trying to predict the next state from the current state given an action, and also the reward of that state action instance. Yeah, sorry.
What about those weights for the intrinsic motivation? You determine them in advance, or?
The ETA?
Yeah.
Yeah, that's a good question. So basically there's a T because I mean it's I actually skipped to the slide, but we'll see it in a second. So basically these are, if you augment the rewards with intrinsic reward and you have some like hyperparameter eta, what you're doing is just basically solving a constraint optimization problem. So and the constraint optimization, like the idea behind the constraint optimization problem is I want to maximize the environment's rewards subject to some like level of exploration eta, essentially cumulative. So essentially, if we were to like basically follow this design, this should be something that amounts the single, like the individual one should be something that amounts to this coefficient here. In practice, this is quite a nuance, because what people have been doing with this is that they decay this parameter as the like based on T. So as you basically explore more to the environment, you're trying to squash this thing to zero. But the problem is that like sometimes people use like we'll see in a second, but like sometimes people use like variance-based sampling. And in stochastic environment, this thing is not guaranteed to go to zero. So what they do is that artificially squash it to zero, essentially, which is like in some environment is good enough. In some other environment, it doesn't really work. But yeah, this is how you said it. But it's just like I think it's like there's some like hyperparameter tuning to be done here, unless you design RI in a more clever way, essentially. I think, yeah, I've basically said most of the stuff. So basically, the difference, just to like note on the difference between model 3RL and model Bayes RL. So model 3RL is just a collection of the approximate dynamic programming solvers for MDP problems. Some people actually use like what is popular nowadays is DeepRL or other like strains of that, or like they call it DeepRL, even if they're using, for example, Gaussian processes priors. And it's sort of like contrast to the model-based RL approach instead. So the model-based RL is where as I said before, like a model for the environments and rewards is used, is either learned or given, or learned with some like inductive biases or strong prior knowledge, which is always the case. And is used to actually do planning, to actually like look ahead and try to predict the sequences, like the downstream effect of sequences of actions. So the way these models are usually learned is, as I said, like by inducing some inductive biases. This can be like, for example, like most of the time it's actually physics dynamics. So this can be done, for example, through Gaussian process priors. So you can have like priors on the mean of the Gaussian process, but also on the covariance matrix of Gaussian processes. But it's also done, I think, in like neural networks with some like physics informed neural network through specific loss functions. Yeah. So just to stress that, like, this is rarely learned from scratch. This is where like the kind of like Bayesian approach through Gaussian process prior is quite useful. Right. I've kind of like already touched on this. This is just like a proper representation of what the problem, because people have been doing this for quite a while, and then they realize, well, but what is this? What is the problem that we're trying to solve here? And what the problem is it's essentially a dynamic constraint optimization problem. Now the issue is that this problem is not really the original MDP problem, because what we're doing in this kind of problem is we're biasing the MDP reward function. So we're biasing also the value function that stem from the MDP. This is good. I mean, it's not crazy, because it was just like trying to nudge the agent to learn more about the environment. But ideally, if we care about either if we care about only exploration, like pure exploration environments such as the Mars rover, but also if we care about good combination of exploration and exploitation, we would want to design this intrinsic reward carefully, in the sense that we want something that obviously like signals truly novel states, state action pairs, and something that actually like goes well, at least like theoretically is guaranteed to go to zero at some point. It will never probably do, but at least this is a guarantee that like in faithful, this is like a problem solving that is faithful to the original MDP, in the sense that like once we have explored enough, the urge to explore vanishes, and we're just like going fully exploitative for the task design by the original MDP. So in a nutshell, we want something that separates well aleatoric and epistemic uncertainty, such that it's the case of sequential experimental design, and we'll see it in a minute. Sorry. And so a good, these two slides are basically presenting a good formulation of the problem, because one can theoretically say that you're biasing the original MDP, so what you're learning is not really the original MDP. You're learning something else. And we found that this different formulation of MDPs, which is Bayes-Adaptive MDPs, are actually a more principled way of representing the problem, because it kind of like together with like the dynamic constraint optimization representation of the problem, it kind of like balances well, or represents well, the balance between exploration and exploitation. So the catch here is just that, again, I apologize for the crude copy and paste, but the catch here is that instead of having states that are purely defined by the environment, we include as hyperstates also states of the theta parameters of the transition distribution. This means that basically everything gets parameterized by. Here's what I found. Sorry, I don't know what happened here, but everything is basically parameterized in terms of theta, and is taking into account the hyperstates rather than the states itself. And why is this nice? It is nice because when we get to the bottom of the MDP definition, we can sort of like define a total reward function, and then we have from the hyperstates, but we can separate it with like extrinsic reward function that is strictly generating from the actual states of the environment, and a intrinsic reward function that is strictly stemming from the parameter of the environment dynamics. That is basically what we're trying to learn through effective exploration. Well, now for people that know experimental design very well, this is probably like 101, like experiments 101. But essentially, like, what is a way, once we have like good definition of what the problem looks like, what is a way of defining a good intrinsic motivation function? And here is where we borrow from sequential experimental design, or Bayesian optimal experimental design in general. So we have theta, which is our parameter of interest that underlies the dynamics in the environment, and we can we can decompose the total entropy of a random variable with respect to another by separating the conditional entropy and the information gain. Sorry, what would be the information gain, but the mutual information. So the total entropy of a variable is basically decomposed into the residual entropy that we see in a variable once we've observed every possible realization of another value of y. So that's basically uncertainty that we cannot reduce any further. So it's like embedded in the statistical experiment, essentially. While so it's a good measure of aleatoric uncertainty. So again, just pure random noise in statistical experiments. While the mutual information instead carries basically all the measures all the uncertainty reduction that we can do by observing y reduction in the uncertainty of theta by observing any possible representation of y. So if we obviously like condition everything on some arbitrary data set, we have like information gain, which is basically what what is the objective also of Bayesian optimal experimental design. Because just as a note, like Bayesian optimal experimental design as a framework is more generally trying to reduce some like utility function around the uncertainty. So some kind of like utility function that is based on the uncertainty around the parameter. But obviously there are like different ways one could do that. Like you can look at variance-based sampling. You can look at like, for example, like prediction error, other stuff. But like obviously this is why people use information gain essentially, because it's the only way to get a faithful representation of the epistemic uncertainty of a certain random variable. Again, this is also like used in Bayesian active learning literature, less so in Bayesian optimization, which uses different things. So the last thing we do is that we basically replace everything and we adjust information gain to look like something that we could use in the MDP context. So the full information gain is based on the full one-step transition ST, AT, and ST plus 1. So this is kind of like, again, the reason why information gain is a good measure is just because essentially we're guaranteed that this thing goes to 0 at some point. We also have the smallest variance as a measure of uncertainty. I think it's been proved by some seminar. I don't remember the paper now, but essentially it's something that in an RL like sequential exploration context is something that somehow, like at some point, will be going to 0, at least theoretically. Then again, it might not be the case, but it's still like a good indication of where epistemic uncertainty lies in the environment. Obviously, like this thing is this property, although it's just like a theoretical property that it's quite hard to achieve, guarantees that informally the Bayes-Adaptive MDP actually converges back to the original MDP. So at the end of the day, this means that the agent will revert back to actually fully exploitative mode. So it means that once he's learned enough about the environment, they will just try to optimize for the policy that gives the highest rewards, extrinsic rewards from the environment. Essentially. Obviously, like, well, I mean, this is kind of trivial, but basically this goes to 0 depending on how complex the problem is. Like, for example, if the dynamics looks like something like this. It depends on the smoothness of the function, the sparsity as well. Possibly if you're looking at minimax contraction rates, for example, and so on and so forth. Also, bear in mind that the other difference with possibly like sequential experimental design is that this is multi-objective. So like this is multi-output. So generally we have multiple states representing the global state of the system. Now, the problem with obviously the IG, the pure IG, is that we can only, as I said before, for stuff like prediction error or empowerment, we can only compute it in retrospect. So what happens is that in theory, like the agent says this transition, right? And then in retrospect said, like bumps into something new and then say, oh, this was actually quite novel. I might revisit again in 1,000 steps. So it might actually go back again to that point. And this is like kind of like the idea of like reactive exploration in RL rather than active exploration. So again, faithful to the Bayesian optimal experimental design or sequential experimental design objective, we can take instead a surrogate measure. So we can basically marginalize out. We can marginalize on the next state and have some form of expected information gain. So this is obviously the expected reduction, rather than the reduction itself, is the expected reduction in entropy by taking a certain action and observing a certain state. Again, this is a reduction in entropy in the theta, so in the posterior distribution. And so the problem with this one, which is obviously present also in sequential experimental design, is that we at each step, this means that we have to compute the posterior distribution, which might be on closed form. So we have to resort to like whatever method, MCMC, variational inference, whatever you want really. But the thing is, like, also we can flip this by using Bayes rule. So we can basically you can easily show that you can flip this from the posterior distribution to actually be computed instead on the posterior predictive distribution, which is sometime when the objective is purely predictive, such as in, for example, Bayesian optimization and Bayesian active learning, then you might want to, in some ways, like bypass a posterior computation to get to the posterior predictive. Like, for example, this is something that they do in image classification with neural networks. So you don't have a posterior distribution there unless you're using Bayesian neural networks. Up to you really. But like what you're really looking for is the reduction in the prediction in the predictive uncertainty, basically. And this is like just showing that theoretically, at least, they're using the posterior predictive is equivalent. Now, we still have some issues, of course, that we carry from sequential experimental design that I haven't addressed yet. Before I do that, this is just a slide reminding of what I just said, basically, and also is giving you like a lot, like kind of like bit of options to use for the dynamics model. So, for example, you have usually Gaussian processes are the gold standard because you can basically get, if you assume well, you can use like a robust Gaussian process, but basically, if you assume that you have everything is normal, then you have a closed form analytical posterior predictive computation. So you can just like, this would be a normal distribution, this would be distribution, and so on and so forth. And the problem with Gaussian processes is that they don't scale particularly well. So you can resort, like we've used some more scalable options that are sparse input Gaussian processes, which are basically trying to, through variational inference, trying to learn a representative subset of a sample size of a sample that basically delivers the same, approximately the same function approximation. So it's trying to basically reduce the scaling with respect to the sample size here. So you would have, instead of having n points, you would have m selected points, and also a test time. You still have to scale quite badly with dimensions. And this is where we use deep kernels, which I don't know if you're familiar, but deep kernels are basically something in between neural networks and Gaussian processes. So what they do is that they use a neural network to reduce the I-dimensional input space to go into a lower dimensional latent space, and then they place a Gaussian process on that lower dimensional latent space. So in that case, you would have like m to the cube, and then you would have something like h to the cube, where h is the dimension of the latent space you're going to. And then obviously there's what people basically do in RL is just chuck a deep ensemble, which is just a combination of it's a collection of separately initialized neural networks that sort of like roughly approximate posterior predictive distributions. Well, I just say I always anticipate my own slides. Seems like I actually wrote them. So this is what anyway, this is what deep ensembles are doing. So basically, you basically start a probabilistic neural network. So you have a parameterization of the mean and the variance based on, in this case, state and action, but based on inputs. And you have a collection of m different neural networks. And so each one of them actually has outputs a distribution. So you basically have a mixture. You end up with a mixture of m normal distributions that very roughly approximate the posterior distribution. So basically, you can do this marginalization. You can do like Bayesian model averaging by just doing a Monte Carlo of a mixture. Sorry, just the average of this posterior predictive, or each posterior predictive. Yeah, so they're quite, so deep ensembles have been shown to work reasonably well. They're like computationally cheap, quite attractive. They work quite well, particularly for a problem where you have tabular inputs, so like people doing image classifications or working on graph based data. So like any kind of non-standard inputs that necessitate some like uncertainty quantification. In the particular case where we use, I generally use Gaussian processes for this. I'm not saying this because you're, I'm Bayesian as well, so sort of, I guess. But again, like deep ensembles are quite popular in this case because they're quite effective. We can prove if we were to work with deep ensembles, which can be popular if, again, we have, so for example, the input space is not tabular. So we have, like, for example, image representations of the state space. We can easily use deep ensembles. but we can show that the expected information gain in this case can be computed as the Jensen-Shannon divergence between the models in the ensemble. So this is just a divergence computed on the mixture of m different models, essentially. So they call it disagreement sometimes. So this is something that they use quite often in the Bayesian active learning, but we can show that this is equivalent basically to expected information gain. Right. I mean, this is quite a stupid slide, but this is why variance-based sampling method fail usually. And the reason is that it's very likely that in RL application, particularly physics RL application, you have heteroscedastic noise. So for example, think about, we'll see an example of a very, very simple toy simulator of a car driving up and down a mountain. But if you think about it, there's probably more, the noise is likely to be heteroscedastic at high velocity. So there's more chaotic dynamics when you're at high velocity. So that's an example where you have noise that is dependent on the state you're in. And if that happens, obviously, if you use, this is the case using deep ensembles, but you can use whatever model. But basically, for sampling purposes, in the case where you have homoscedastic noise, then the variance of the approximate posterior is basically signaling same regions as the predictive entropy as novel region, or pretty much the same. By the way, this is negative because differential entropy can actually be negative. Entropy should be always positive, but I say this because when I saw this, I was like, why is this negative? But this is actually a continuous distribution, so it's so it can be actually negative. While in a case where we have a heteroscedastic noise, the signal is quite mixed because here in the middle we have high variance, we have low variance here, and then we have obviously high variance here. But here is just high aleatoric uncertainty. Here is high epistemic uncertainty. But something like predictive variance or predictive entropy doesn't really distinguish the two together. So while disagreement actually does. So and the catch is here you have of course a lot of disagreement between the ensemble predictions. Here you have high individual noise. So this thing will be high for all the networks, the neural networks. But the mean will actually agree. So you don't have much disagreement between the means of the ensemble. Right. So I'm left with 5. I'll keep it short. But basically, the 2 slides, I think we'll build up all these things to actually tackle the 2 problems with sequential experimental design for RL. So one thing is the short-sightedness, as I said before. So if we have a model of the environment, provided that we have a seemingly accurate model for the environment dynamics, then how can we actually harness it to see what are the downstream effects of taking a certain action at the current state? This is something that sequential experimental design in naive form doesn't do. And the other thing is actually quite a popular trend also in sequential experimental design to amortize sequential experimental design, is that the problem again is that even if we sort of alleviate some of the computational burden with the posterior, bypassing the posterior computation, then we need to re-optimize for design at each step. So we have to compute the posterior predictive in this case. So we don't need the posterior, but we need to compute the optimal design. This is like first, second slide at each stage. So each stage is a different optimization. So to avoid short-sighted, so the first problem, avoid short-sightedness, we can actually use the model to roll out trajectories. So these are just like predictive Monte Carlo trajectories for each steps ahead. Also, you can basically adjust the J based on the uncertainty of your model potentially. But this is just building a sample of predictive trajectories from the current state. So imagine this car, just like imagining where it would go, and by sampling from the dynamics posterior distribution, and then of course in purely the rewards are in purely explorative settings. The rewards are just a cumulative expected information gain of this predictive trajectory. So this is quite cool because we're not just looking one step ahead. We're not being myopic, but we're also looking down the line what a current action will lead us in the future. Obviously, you can also have extrinsic reward if you have a reward model, but we're interested in purely explorative tasks. This is the mountain car example. So that basically, like, imagine like this toy environment where your agent is dropped. Your agent is the car, but it's dropped in the middle, so it starts like oscillating here. If you're using like reactive exploration, so just in one step ahead, or one step ahead, or reactive information gain, it will take a while to actually bump into novel states and then try to push up and down the mountain. So the goal is actually reaching the flag. So you would have to counterintuitively go up first and then gain enough velocity to reach the top of the mountain. But we can sort of like be very sample efficient if we had learned a good model of the environment. This is actually also physics-based. So we can actually like draw this, like roll out this trajectory that sort of like sees where the car will go in the future and try to optimize the current action for the old trajectory instead. The way we solve for that trajectory is the other point, the last point that I will try to talk about, is that some people usually do, well, historically people have been doing random shooting or SEM. Random shooting is just basically, I like the analogy is just basically like you throw darts at a dartboard and then you pick the one that is closest to the bullseye without even aiming the bullseye. So this is just like computationally cheap because you sample a lot of stuff without doing any intermediate like optimization. While SEM actually tries to narrow down, starts with at every step starts with a distribution and start sampling from the distribution and then narrows down the distribution by reweighting. But both of this actually do this every step. So we want something that we basically can parametrize. So we want a parametrized policy that we can. So instead of like optimizing the design at every state, which is very computationally cumbersome, we just take a few gradient steps towards the objective in the policy parameters, and then we use the policy to sample the action. This is obviously better than re-optimizing at every stage. So we don't have to do it at every stage if we don't want to, but also we don't need. It's actually cheaper to have to do a few gradient in this space than doing full optimization here, and you end up with good results anyway. Right. This is just a couple of very simple experiments. I'll just do this to run out of time. So this is a simple mountain car example that we showed before. So the BAE is this predicted trajectory sampling plus policy optimization, and here this is just sort of random exploration and some like very naive. This VIME is using basically sequential experimental design, the same thing, almost the same thing. Sorry. While these things are actually our methods, they look at methods. This is looking at only 5, and this is looking at 100 steps. So, and this is like the fraction of states visited, so the position of the car, essentially. So if you did like, this is obviously computationally a bit more cumbersome than this, but it basically solves the environment in 200 steps instead of basically just roaming around the car, roaming around. Yeah, I mean, the last thing is to go back to the question that we had before. We are actually looking, potentially looking into something like this, which is actually a version of like safe exploration, where you try to maximize the cumulative expected information gain, but under some cost function that is defined by environment. I put dynamic treatment regime, but I think this is not something that people actually use in dynamic treatment regime, but it's more like robotics. This is like safety borders in robotics, for example, and so on and so forth. Right. Thank you.
Are there any questions online or in the room? Perhaps I can ask something.
Yeah, sure.
You added this term, expected information gain, and you showed that it's just becoming irrelevant as the sample size increases, right? Oh, there's a correspondence with the MBP solution.
Yeah.
Necessary that this theta parameter is static, like happens if it changes over time.
Yeah, I mean that's obviously one of the underlying assumption in the classic NDP, but also in the other specification of the NDP that are built on the classic definition, is that everything is stationary. So you have like stationary rewards, you have stationary transitions, but also you don't have time varying theta. But in that case, I guess you would still, well, I guess it depends when you have this like regime switch. I'm trying to think whether that could be a problem or not, because I think like I'm thinking of a situation where like the parameter switches could also like switch randomly, but in that case you would want to, so that would trigger bigger updates of the posterior, because you're basically moving away from your starting distribution, posterior distribution, and that would result also possibly in higher expected information gain. But this is something that you probably would want, because you're trying to learn, like relearn the parameters of the well, at least in the exploration side of things, but then like obviously your model would be wrong at the beginning. So when you roll out trajectories, the trajectories might not be extremely faithful. Yeah.
That makes sense. Thank you.
Yeah, sorry, I was trying to.
I just recommend that given the time, any outstanding questions, everyone is welcome to stay for additional questions online or in the room. Everyone who is engaged in the meeting afterwards, let's thank the speaker again.